He would put aromas in the room at the jail, and he had a big flip chart, and he would explain to the prisoners that even though they were in prison, maybe for their fault or because somebody else had done something, they still had their identities, their consciousnesses. Those could not be taken away from them. They could build on their identities. And I thought about it and I said, you know, it's just like an electron. Now, being a physicist, I thought about electrons. If I were a poet, I would have thought about a poem, or a musician, I would have had a song. But it occurred to me that you cannot destroy an electron either, just like you cannot destroy a human consciousness. The electron can go backwards in time and be a positron, or sometimes it can be a neutrino, but you cannot break the word line of an electron. So I thought, and you know something else? The human consciousness, which can't be destroyed, is even more like the electron's wave function. I'm doing all this thinking during this weekend in May 2000. Next one, please. Now let's imagine we've got a wave function. It's a wave packet which describes an electron. Now, if you took this wave packet and you took a quick picture of it, the electron might be there. Another instant it might be there. Another time it might be there. But if you took 1,000,000 pictures just like that in a hurry, you would find the electron was along one of these lines. That's why it's called a wave, because it creates a wave. Now, why the electron disappears and starts up again is something that nobody knows, but sense says that particles appear and disappear, appear and disappear all the time. We're just not aware of it. Anyway, the electron has a wave function. And if we go to a wall with a couple of slots in it, then the wave function coming out of the wall starts emerging like this, two hemispherical waves. So now the electron might be there, it might be there, it might be there, it might be there. Now, next slide, please. Rosalind Haywood was the psychic. She was married to a British diplomat, and she wrote a couple of books. She was a very famous psychic. And one of the books she wrote was a personal memoir. And she told a story. She said it was a hot night and her husband and she were visiting her husband's cousin. And they're in this big bed. And she is amorous and he is dead tired and asleep. And she wants him to wake up and make love to her. And instantly, at the end of the bed, her same person appears. Her same self appears here in a white nightgown. She's in a pink nightgown. Here she's fully aware and sees all of this and thinks and so forth. Here she's fully aware and sees all of that and thinks. She's in two places at once thinking at the same time. And she said, all of a sudden, this white me said, you silly fool, you know your husband is dog-tired, leave him alone. And she said, back to the white me, I'll do as I please, you pious prig. But she was angry because she knew that this was the stronger. And then all of a sudden, boom, she's back in herself again. And I thought, that's just like an electron, because, previous slide please. Here's an electron with two wave fronts. Other slide again. Here's Rosalind Haywood in two places at once. So we have a consciousness in two places at once, just like a wave function going to be in two places at once. Okay, that was my first thought. Now I had another thought. Well, I'll skip that and go to the third thought. Next slide, please. What the heck? Where's my wave function? Oh.
No, it's not there. Is the next slide? No.
It disappeared.
Yes.
Let's go back. Well, what I had drawn here was a wave function where one electron is spin up and the other is spin down. Here it's the first electron is spin down and the second electron is spin up. What you do is you produce a couple of electrons in an isotope, in an angular momentum zero state, and they separate. And their wave function has these two terms. This guy spin up, this guy spin down, plus another term minus this guy spin down, this guy spin up. Now, it's impossible for these two configurations to exist at once in physical reality. They're physically impossible. They can't be both spin up and spin down at the same time. But in wave functions, physically incompatible configurations are very common. In fact, that's usually the case. And it's the case here, where you have to imagine this wave function. Now, we're going to let these two electrons separate like this. And now I'm going to have a Stern-Gerlach apparatus over here, which can measure the spin. You can tell whether the spin is up. If the electron moves up like that, it's spin up. If it moves like that, it's spin down, because there's two magnets there. And so let's say that the electron comes over here and it's spin up. Then the second term, which had the electron spin down, disappears instantly. We're left with just the one term, where this electron would spin up and that would spin down. So if that spin up, then this particle here immediately has spin down. And not only does it have spin down, but it has spin down much faster than light could carry the message. They could be a light year apart, but it would happen instantly. You say, how do you know that? I say, well, there's this physicist, Mr. Gisin, G-I-S-I-N, at the University of Geneva in Geneva, Switzerland. And they took commercial telephone light pipes, the fiber that they use, fiber optics, amounting to some 20 kilometers, and they did coincidence tests, not using electrons, but using photons. Now, photons have spin 1 h-bar, just like electrons have spin a half h-bar. So they used the photon. And they would detect photons that had been produced once again in a spin 0 state, so they had the same kind of funny wave function. And when they detected one photon, they checked the other one, and it had spin down. And either that would spin down instantly after this one was detected to be spin up, or it would spin down either 1,000,000 times faster than light could carry the message, or 1,000 times, depending on whether for their coordinate system they're using the Ural Mountain as their base, or the Big Bang Center as their base. So we know that these signals go very fast. Okay. Now, I remember reading a long time ago about twin sisters where one had suddenly felt the effect of a plane accident on the other, and I looked around, and you know, Google is wonderful, because I went to Google and I looked up Tenerife, and there it was. The whole story was laid out in Google. They were using it as a case history for the law school at the University of Nevada in Las Vegas. 1747, a Dutch 740, this is in 1976. And this Tenerife is one of the Canary Islands, but it was not fully equipped. It had landing strips and all, but they didn't have radar working. There was a fight going on in the main island, and so planes were landing over here. And this Dutch 747 had been delayed about 8 hours, and the captain didn't want to wait any longer, because then he would have to stop the flight for the day and start over the next day. So he was anxious to get going, and his co-pilot said as they were starting to take off, "We are at takeoff." He didn't say we are taking off, or we might have saved 600 lives. He said we are at takeoff. Meanwhile, there's a Pan Am 747 landing, and it's foggy. They can't see each other, and the radar isn't working. And so the pilot of the 747 with Pan Am hears this radar, hears this talk on the radio, and he's getting nervous, and he actually drives the plane off the runway part way, but not enough. And the 747 crashes into it, and the two planes go up in flames, and something like 560 people died. One of which was a lady whose identical sister lived in Fremont, California. And at the instant of the crash, the twin sister, or identical twin sister in Fremont, falls to the floor of her kitchen, feeling like she's being torn apart and burned up. And the other sister, in fact, was being torn apart and burned up, I presume, because he was killed in the crash. The sister in Fremont tried to sue Pan Am for damages, but the judge threw it out because she wasn't there at the accident. But it made it in Google, you see, so I had my reference. So here we have a case where, once again, two electrons are joined somehow, and two consciousnesses are joined. Next slide. So I said to myself, I hypothesized that the electron wave function is conscious because they're aware of each other, the two electrons. And the human consciousness is a wave function, which makes sense too, because everything's a wave function. And therefore, I propose an experiment to see if a human consciousness could interact with an electron consciousness. That was the idea I had in Rye, New York in 2000. Now, being a physicist, I have an experiment. You see, like I said, if I were a musician, I would have written a song, or a poet, I would have had a poem, but I'm a physicist. And so next slide, please. So here's the experiment. A human acts on an electron which is spinning, let's say, counterclockwise. We'll represent that with this arrow down. And the idea is that this person, or this person uses his or her mind to flip the spin up. Now we put it in a weak magnetic field, 50 Gauss magnetic field, 100 times the ambient electric field, magnetic field. We put it in a weak magnetic field to define the direction, and it takes a little energy then to flip the spin. It's like taking a compass needle and moving it against the direction of magnetism. And in a 50 Gauss field, this would take less than 1 part in a million of the energy of a single photon. That's such little energy, you'd say, can this possibly be stable? But it is. You could slam a lab door and it wouldn't flip this spin. You could flip the spin by carrying a magnet around, but if you didn't do that, it would be very stable. Now, I talked with Joe McMonagle years ago. They were doing an experiment at the Stanford Research Lab. They were wanting to see if they could change the rate that a spring was oscillating, and they were putting it inside some kind of packaging which was suspended, and putting that inside more packaging, to keep trying to get rid of vibrations. And they finally decided it was going to cost $250,000 to get this pendulum suitably insulated, so they gave up. But this guy is 20 orders of magnitude more sensitive, and it's stable. By 20 orders of magnitude, how can you compare that? That's like taking a little vial of dye and dumping it in the ocean and letting it circulate around. And you in Australia, you pick up the same amount of water and it's got 80 of those little dyes in it. It's an incredibly small number. Okay, next slide, please. Is there any reason to believe that a human consciousness can flip an electron spin? Yes. The famous Chinese physician and psychic Yan Xin altered the Raman spectrum of water at a distance of 5 miles. If you're not familiar with the Raman phenomenon, take a test tube full of water and shine a yellow laser light through the test tube. Coming out of the test tube will be mostly the yellow light, but a little bit of light of slightly different color. That's the Raman effect. And Yan Xin was able to change the Raman effect and increase it by about a factor of 20, just using his head bone. And he was 7 kilometers away. He was going to do it at the university in Peking, China, but he couldn't make it that day, so he called over, and the Chinese professor of chemistry that was looking at this phenomenon, organizing the measurement, was disappointed. And Yan Xin said, "Oh, don't worry, I'll do it from my house." And he did. They had 4 test tubes there, and the 2 controls and 2, or was it 4 and 4, and he left the control tubes alone, and the other tubes he created this Raman effect, and it was measured by a technician who didn't know what they were doing and just did his job, and they took the measurement. He also apparently was able to change the lifetime of americium-241 by 9 standard deviations. That was just 1%. You say, well, what's 1% difference in the standard lifetime? Yeah, but it was 9 standard deviations. And he was 1,500 miles away at that time. Next slide, please. So, is there any evidence for a field which links one consciousness with another? Well, there's Yan Shen's Qigong. He's able to cure people just using his mind. That's another story. There's Bob Monroe and his M field, where he goes out of body and uses the M field to communicate. There's Rupert Sheldrake's morphic field, and Rupert Sheldrake was at that conference in Frankfurt in April last year.
Quantica.
Yeah, he went to the, and then Wilhelm Reich and his work on energy field, and finally the Slater Salter's 5-dimensional life energy field, which is a whole other story, so I won't go into it this time. Next slide, please. Little history. How am I doing time-wise? Good.
Way over, but don't worry about it.
So in 2000 I had this idea about flipping the spin, but I didn't know how to do the experiment. And in 2001 in the fall I was in Holland on a sabbatical at the University of Nijmegen. And I'd been to the Monroe Institute and learned how to meditate. I had some time there at Nijmegen, and so I wrote down the names of about 45 physicists who were in the department at that time. Now we've got 65, but then we had just 45. Still a big department. And I wrote down all their names, and the first guy's name I wrote down, I put a big X by his name. I know he'd be no help in finding an experiment. Then I looked at the other names and made little marks, question marks. Then I meditated. I went to a thing that they call Focus 12 at the Monroe Institute. And I said, who would help me make the experiment? And the name came up instantly. This guy who I'd said would be no help at all. That's David Church. Would be no help at all. His name came up. I said, well, okay. So I got back to the States and I went and talked to him. And sure enough, he was helpful. He talked for a full hour describing the experiment, how you would do it. And which we'll hear about later. But anyway, so then I went and studied, because I'm not an atomic physicist, so I studied for about a week and I came back with a whole bunch of questions, and he spent another hour with me. And I went and studied for another week, then I came back with another bunch of questions. He spent a third hour with me. And finally a fourth hour just talking back and forth on the phone. And I had all my ducks in a row now. I knew exactly what to do. And he said, now I can't do the experiment, but Hans Schuster can. He has the equipment. So I went to see Hans Schuster, and I told him this story about, you know, making the spin flip and how we set up the experiment using the lasers shining on the ion in the ion trap, and he scowled. And the more I talked, the more he scowled. I thought, oh my God. So finally he looked up and he said, well, if you can find $30,000 in a grad student, I'll do it. Now here we are in deepest Texas, a very conservative university, and psychic work is a kiss of death to physicists. they would rather, you know, undergo dental treatment without Novocaine. But here I found 3 guys who were willing to work with it, and there was a 4th person. The department head gave us money to do this work with this grad student. I found the grad student, and we worked with her for about a year, but Schuster was away about half the year, and she was too busy with coursework, so it didn't work. But there were 4 of us, me and Schuster, and the department head, Ed Fry, and David Church, that were all working together on this. Well, now things went in limbo, because the student hadn't worked, and we talked about it. We decided we needed a postdoc. We needed a postdoc because people kept saying, if you tell a student who will do this work, that you'll destroy their career. And the student doesn't have the advantage of knowing far enough in advance whether this is the kind of way they want their career destroyed or not. Whereas a postdoc will know how he's destroying his career. And so we needed a postdoc. Plus, we wouldn't have to train the postdoc and wait till they finished taking quantum mechanics. They'd know it already. So we needed a postdoc. There was another little problem. We needed money. And we couldn't advertise for money because it would embarrass the department. Plus, we only knew about the Department of Energy and the National Science Foundation, and we knew they wouldn't give us any money because you send your proposal in, 6 physicists review your proposal, and in that time frame we needed 5 excellents and 1 very good to get any money. We weren't going to get 5 excellents and 1 very good from 6 physicists for this project. So there was really no help. But I gave a talk in 2008 at a meeting in Denver, Colorado for the Seth people. It was the Colorado Seth Conference. And sitting in the audience, when I gave my talk, was Marlo Bendau-Rees.
Hey.
She heard the talk, which had nothing to do with this experiment, but she still liked the talk. Now, Frank also was at the conference, but he was listening to somebody much more interesting. This is a lady that could look at you and tell your whole history just looking at you.
Knew everything about you. Yeah. She understood your whole lifetime just by looking at you. It was very awkward for her because you meet someone and you know everything about them, all their current problems and all their past problems immediately. So.
So you went to the
So
I thought Ron was more interesting. And I was right.
So then I visited them. I had the pleasure of staying overnight at their home in 2009 up in Portland, Oregon. They got a house which goes up many stories, overlooking the beautiful Portland and the mountains and everything. And we talked a little about the experiment at that time. And then I went back to College Station and, you know, with no money and no student and general negative response from my colleagues, things weren't going very fast. And then Marlo got to talking to Frank. And she wants me to be sure to mention that she had a hand in this because she did. She was an inspiration. And in 2011, in the fall, Frank suddenly sent me an email saying he was going to fund the experiment. Who could believe this? That same spring, I'd given a talk in London, in Oxfordshire, England, at a meeting of the Brahma Kumaris. And I described the experiment at that meeting, and sitting in the audience was none other than Thorsten.
Marco.
What?
Marco. He was also there.
Marco did, okay. Yeah,
And it
right.
was Marco who told me to talk to you to see what we can do.
Ah.
Ah.
And you also
But I also liked it very much.
Yeah, right.
Care about it.
Good. We have something in common.
That's right.
Now,
Well, I'm
why,
glad you remembered Marlo.
And Marco.
And now Marco, yes.
now, why was I giving a talk in 2011 in Oxfordshire, England? Because I met a lady at a previous meeting, this Rye meeting in 2000. One of the ladies there was Drosela Elliott, and she invited me to a Brahma Kumaris meeting in Mount Parnassus near the Oracle of Delphi in 2004. And Thorsten was at that meeting. In fact, I learned later he was one of the organizers. Well, so coming back to the Oxfordshire talk, meanwhile he'd gone to the Technical University in Berlin, a fine institution, gotten a PhD in experimental atomic physics, exactly what we needed for a postdoc. And there he was at the top. And then a few months later, Frank Rees says, "You'll fund the experiment." Talk to Schussler, he says, "Fine, we'll do the experiment." And So the arrangement was made, and Marcus Fromm was going to come along and be our laser man. And so they were going to come in June of 2012, and they did, but meanwhile, we had a new department head. And the new department head said negative things about the experiment. He was not only non-supportive, he was almost booting me out of the department.
Pseudoscience.
So, yeah, he called it pseudoscience. And so Schuster was so upset that he left the project. But without Schuster, we wouldn't have gotten started ever. He played an important role. It's like when you hitchhike across the United States, he was the first 1,500 miles. I mean, it was essential. It was essential to have Schuster, even if he didn't save the whole trip. And so, we'll go to the next slide, please. So, when the department head said negative things about our experiment, and Schuster said he didn't want to be part of it anymore, except he would continue to see Thorsten and Marcus for the month of June, like he'd promised. Thorsten and Marcus had this idea, we moved the experiment to Berlin, to this lab here. And I mean, who would have thought there would be a lab available for this experiment? And the incredible thing was not only that, but they also had salary from Christian in Vienna. I couldn't believe it. All these things are coming to pass. And Frank upped his offer by a factor of 3 to pay for the equipment, which we would now have to buy for ourselves. But what I can just say, it was just an amazing turn of fortunes, because now Thorsten and Marcus were going to be working in their own lab away from Schuster, who would have provided guidance, and away from all of his equipment, which they're now going to have to buy themselves. And they made this leap. Well, here we are, and they're doing it. It's just the most amazing thing. We have a lab provided by Hagen Ruff, who lives in Miami, Florida. Salary provided by Christian. And apparatus and travel provided by Frank. And it all came together. It's just the most amazing thing.
I would like to say at the 2011, that, of course, as I offered to fund the experiment, it was only, I don't know, $10,000 or $15,000 at that point. It's in trouble because we had all the equipment. That's why we were at Texas A&M. There was only a little bit of travel, and we had to get the physicists there. So
no, it was 50, Frank.
Was
You
it
offered
50?
50,000. Yeah,
50,
yeah. We were going to do it. We were going to do it.
It was. It's a different scale today with the equipment being here. It was much easier what we were going to do.
Well, we were all gung ho, you
Yeah.
know. Next slide, please. Well, this is my last. I just want to say that what we're trying to do, of course, is determine if consciousness interacts with matter, and I'm going to assume that it does, because there's so much anecdotal information. The trouble is, it's never been done scientifically on demand, in a way that physicists would understand and appreciate and believe. Because we want this experiment to be reproduced to other labs around the world, so that it'll become part of the thinking of physicists. Now, back in 1865, Maxwell put together the 4 equations of electromagnetism, plus an extra term of his own, and discovered his equations would create waves, which of course we recognize as light or radio waves or heat waves. Electromagnetic waves were then predicted on the basis of uniting electricity with magnetism. And they even were able to predict the speed because of lab tests on magnetism in the lab and then electricity in the lab. They had certain constants which arose. You multiply 2 of these constants together, it's square, and anyway, you come up with the speed of light, and sure enough, that's the speed of the electromagnetic field. 3 times 10 to the 8th meters per second, 186,000 miles per second. Well, I think that when the consciousness of a person affects the electron in our experiment, the attention experiment, it will be mediated by the M field. which is much faster. If this is so, we can begin to look for theories integrating the M field into the interaction between consciousness and the electron. And this will add basis then to things like Reiki, where one consciousness works on somebody else's mind. If it works on the electrons in their brain, it probably works on their mind too. This would also work for distant healing, because psychic phenomena don't care about distance. So this M field is not only tremendously faster, but it's targeted. It doesn't weaken or get distorted. Now,
Right,
excuse me?
right.
Go back a couple of slides. Go back one slide. 2 slides. 3 slides. I'm sorry, I couldn't think of Wilhelm
Wilhelm
Reich.
Reich, yeah.
I couldn't think of it for a moment. Wilhelm Reich predicted that the human consciousness could affect weather, and he developed a machine that would do that also. Here's another thing. Some psychics talk about getting messages from the Pleiades, and you say, well, that's fine. You can stay in this asylum here if you like. But if these consciousnesses in the Pleiades, which is about 400 light years away, are really using the M field, well, they probably could interact with our machine. And instead of waiting 400 years for the message to come this way and 400 years for it to go back again, which is very slow communication, it could be done in real time, because the M field is almost instant. So in our machine, we might be getting some interesting messages from distant places. And finally, so little energy is required to flip the spin that I suspect that if somebody went out of body, you know, like they teach us how to do at the Monroe Institute and places, I suspect that if somebody went out of body and boogied over to our lab, they could flip the spin out of body. It's 1/1,000,000 to 1 electron volt, and Seth says, where there is consciousness, there is energy. Now, physicists don't believe that there's energy coming out of the mind much, because they've made measurements, they don't get much. But we're not talking about a lot of energy, plus they're not measuring the right field anyway. It's the M field they should be measuring. So I don't think there's any evidence against the fact that the M field consciousness might carry a small amount of energy, and very little would be required. And for that matter, let's take a human person who goes out of body and then it stays out of body. They could still probably do it. And so my mother-in-law, who died in 2006, could maybe send me a message on the machine. Well, finally the M field would act between consciousness and consciousness, which is telepathy. And one last term I thought of after I'd already finished this slide was you could have an electron here and an electron there. Well, let's go to this picture. Here's an electron and here's an electron. And now, this time they're interacting not with the EM field, but with the M field. So it's a whole new physics. One of the problems in astronomy is that after the Big Bang and the cloud erupted, that it's so uniform that they scratch their heads, because you see the 2 parts of the expanding balloon are outside of light range of each other. It takes light too long to get from this side to this side for there to be uniformity. But there is uniformity. Well, they've invented a theory called inflation theory, which I don't like, personally. But we wouldn't need inflation theory. If the astronomers believed that their electrons were conscious and interacting with the M field, they'd have a whole new way of looking at the uniformity of the cosmology. Okay, this is all I'm going to say. I'm finished.
I have a short question. Why is it nearly infinite? The velocity of the M field, why is it nearly infinite and not infinite? Is there a reason for that, or?
Yeah, because I don't want to say something which isn't true. All I know is that the people, G. Sand in Geneva, measured the correlation between photons. And he found that it was either instantly the one was one spin up, the other was instantly spin down, or 1,000 times faster than light could carry the message, or maybe 1,000,000 times faster than light could carry the message, depending on where they set their coordinate system, either the Ural Mountains or the center of the Big Bang. So that's physics. I can't say infinite because it's not been measured.
Electromagnetic signals won't do it.
That's right, that's right. Yeah. Okay, thank you.
So now, I think comes the second part of this point. So I have the chance to. Okay, there's some sound for the recording, but maybe I can introduce a little bit. So now I'll talk about the progress.
Just a second.
I can repeat that. Don't want to bore everybody. Also, es geht jetzt, vielleicht nächstes Slide. Es geht jetzt it's now about the electron intention experiment and how far we have gotten, what's left over, and a little bit on the physical, detailed experimental principle. So, so we start maybe with this picture that Ron also just showed. So we have the human being, and what we want to do is we want to see the single electron spin and see if we can flip it with a mind. And also, of course, we want to see that it's stable if no mind influence is there. So yes, next slide. Bryan just introduced the whole idea himself. So next slide. This is also been referred to by Frank today. So in 2012, so the storage of ions and this configuration with the 4 rods, which is called a linear Paul trap, ion trap design. 3 physicists got the Nobel Prize for doing certain measurements with that. So you don't get the Nobel Prize for the principle, you get it for what you did with it, but it's usually confused. So here, what we see is very important. Here you can see, like with a camera, 3 different dots, and these are fluorescent ions. So in principle, this is exactly what we want to do. We want to have a camera, see 3 dots, and now when we use our mind and flip the spin, the dot should kind of be gone, and if I flip it back, it should shine again. So I'll show a few slides on how this is done technically. So yeah, next slide. So here is shown the principle how the 4 rods kind of stabilize the ion. And so what you need is you have a alternating current that you apply. The light blue and the dark blue are always on the same potential, and the red is kind of a so-called end cap. So there's a DC voltage between the red and the blue to keep them on this line, and the blue ones and this alternating current kind of makes this yellow dot, which is kind of the ions here, stay in that yellow region. And when that all works, you get pictures like this. Here you have maybe 20 ions, and if you wait a little bit, some will kind of fly out after some time, and then you have less and less and less. So this is something that we would enjoy to have, like a line of 5 or 6, so that with the mind we can work on it. And if you only have 1 left, of course, it can also disappear by other means. Yeah? Other means is even at minus 10 or minus 12 millibar high vacuum, still once in a while, maybe once in 24 hours, an atom will hit that ion and transfer an electron, and then it cannot be stored anymore and it's gone.
Or
So-
else it might have an attitude.
Well, we'll come to that later. Maybe next slide. So this is from Paul's work, the guy who invented the whole trapping thing. And what you see here is a ball, and what you see is a so-called saddle potential. So it's like for riding horses, a saddle. So if you turn the saddle, that's what is the idea of the Paul trap. If you turn the saddle, then the ball will stay on the saddle. If you turn it quick enough, yeah. So maybe 1 times back. So the alternating current and this configuration of long blue lines is making exactly that electronically. The saddle potential that turns in 2 dimensions. That's why it's confined here, and the red DC line is confining on the 3rd dimension. We don't want to go into much more detail than that, because 3 dimensions are usually a little bit difficult to imagine, because, next slide, this is only 1 dimension if you look at it like that. Okay, let's move on. So here is like a student experiment, not in the vacuum, but here you have the 4 rods. You only see 2. We have a green laser, and this is some sort of a very light material, some seed or some grain, some powdered grain. And if you do it right, applying the AC voltage, you can test your equipment or can show that this trapping works. Yeah? But in this case, it's not an ion, it's only very physical, and this is only to show how our ions, how it will look like. But we can't see them, so I think this is instructive to look at this picture. And next slide, yeah. So now we want to just briefly talk why are we seeing the ions? And the physicist talks about fluorescence, which basically means energy, in this case photons from the laser light. They come in here, and this is energy levels. So, and they lift the energy of the outer electron of the ion a little bit. So the photon is absorbed from the laser light. You need an intense laser light, so you give a lot of photons to the ions, so they can do it as quickly and as often as they want to. What happens is they are lifted up, and then here this line, they relax the energy again. That's called fluorescence, and they shine it in all directions. So if this is like the laser beam, and the ion is here, and you look perpendicular, if the ion is not there, you will not see any light from the laser. But if the ion is there and is doing this, then you will all of a sudden see it. And it is about 10 million photons per second, because it's a very quick transition, 10 to the minus 9 seconds. So if you give enough laser photons, and it happens quickly enough, you get 10 million photons, which shine in all directions. So if you look only like with a lens and with a camera, you might only get a few 100,000 or a million, but that's enough to be easily detected with the right equipment. Next slide. So this is only for the specialist physicist, I would say, but in principle what we can see here, these are the energy level without a magnetic field, and if we apply a magnetic field, then you all of a sudden have more energy levels. In optics you would have more light, laser lines, more optical lines, and in general we need that to detect the difference between the spin up and the spin down. That's why it's very important for us. So spin up and spin down are these 2 levels here, and these black lines here, the transition, so the distance is kind of related to the energy. This shows that if you're in the upper spin and you lift it up, you end up at this energy level. So it exists, so the fluorescence happens. Now if you're in the lower state, this exact energy brings you only here, and there is no energy level there. So there will be no fluorescence, and there will be, you can't see the ion. So this is how we detect the difference between spin up and spin down of the electron with the laser light. Next slide. Here again this picture where you can see, so if the energy distance is right, you can see them. So if we have something like this with magnetic field, and with a mind we can flip the spin, it will disappear. If we flip it back, it will come back. Okay, so now we'll come to a lot of pictures that you have seen already, but I will give you some more information what you actually see on the pictures. Here is a list of what we have already achieved. We have the vacuum system fully up and running. We produce ions. We have the ion trap. We have the tank circuit that I will come to and show you, which is important. We have the computer control, we have the ion detection, and the optical laser and setup is there. Okay, we'll continue. So you've seen this already. This is the chamber, about this big, where inside we have the ion trap, and this outside here is, and that these two are so-called Helmholtz coils. There's a lot of copper inside, and if you give a high current, let's say 6 amps or 10 amperes, then you get the desired magnetic field inside. So here you see a picture where we started to build up the vacuum system. You see everything is closed. So it's a test run. Next slide. Now there are more pumps attached to it, and the electron guns are being tested here now. Next slide. So again more. This is a tank circuit which came, and some other equipment. Next slide. So then you have here the ion pump and titanium sublimation pump down here that carries you from -9 to -10. And pump in that sense, meaning what you do is, slide back here, you evaporate titanium into the chamber, and then you have a very fresh titanium surface on some parts of your apparatus inside, and then some atoms that still fly around inside the chamber, they stick to the wall, and that's pumping, you know. So okay, next slide. So this little one here is the magnesium oven. The magnesium is a little wire inside this tube. This is a 2 millimeter outer diameter, 1 millimeter inner diameter tantalum tube, and a tungsten wire around it. The tungsten wire, we sent like 7 amps through them, then it glows like a light bulb. That heats up the titanium to about 1200 degrees Celsius, and that melts the magnesium wire inside and evaporates the magnesium. Here's a little hole, and this is for testing, so I can see at what current I'll get magnesium. So this is the electron source for creating electrons. Next one. This is magnesium oven electron gun for testing. Again, same setup from a different angle. In my test setup, which is in a different building, which you haven't seen, I tested the different devices to see how much ions do I actually get, does it work, at what parameters does it work, and so all very important to know. Here we see our trap. These are the main rods in here, the paw trap configuration. This is only for fixing, for pressing the whole thing together, all machined in our machine shop. And these little stainless steel rods are held in place by the manufactured ceramics. This is the think circuit. So basically you go in with the amplified radio frequency, and because the amplifier has an output of 50 ohm, that's the usual output for amplifiers, but these are the Paul trap rods, there's no current flowing, so the impedance, the resistance is extremely high. Yeah? So you need something like to match the impedance of the amplifier with the impedance of your rods. Basically what it does is you come in here with 10 volts and then you have 300 volts on the rods, because that's what you want. And that's how you transfer the 1 watt of the amplifier to the rods. Because what we want is, we want high voltage, high field to contain our ions in place. Next slide. So you cannot buy this, it's all designed, manufactured, and so this is made on our lathe. There's like a screw on top where we then put the wire and so forth. The distance is exactly measured, and they have certain parameters. One slide back. That these are the coils, and they have a certain, basically the coils are important so you can bring voltages, DC voltages, to the different stages. So that on the center axis you can have different voltages so that they stay in the middle and don't go out at the end, and so forth. And one is for matching, and then you have condensers, and in the middle it's more complicated, because in the middle section we want to put in another frequency. Basically what happens, the ions kind of make a movement like this in the trap, a micro movement. So, and that has a frequency, and if you apply exactly this frequency, you kind of kick them out. So you can use that for selecting and detecting certain ions, and that's called secondary scan. Next slide. Next slide. So here, everything had to be cleaned, as I said before. These are all the different parts that after cleaning are all put together. And these are they're not all parts, but most of them. This is our magnetic field measurement. This is a test to see if in the center of our, we get the right amount. And we have here, for Ron in Gauss, 65 Gauss. Because we calculate in millitesla, and so this will be 6 millitesla, but for Ron it is 65 Gauss. And we can apply more current. It's not that difficult, because Ron, the more current you apply, the more magnetic field you get, and the more the levels split. And depending on the laser quality that we get, we need more or less splitting.
Yes.
Which is like, we can kind of play with the distance of the energies, and so, okay, some reserve is always good. This is the whole setup, which is then put into the vacuum system. We have the magnesium ovens, all the electrical connections, and the trap is in the middle. And all these extra fixtures also, of course, had to be made, so everything could be attached to these rods here. Okay, one more. So now this is seen in the vacuum. So the whole thing, don't ask how difficult it was to put it in the vacuum chamber. It's without breaking anything. It was not easy, but somehow I managed. Maybe I think with the help of Marcus, I don't remember, but it was difficult. Okay, next slide. So this is for detecting, it's called the channeltron, and this is for detecting ions. They are reflected into this. This is kind of a tube, and you send in one ion, and you get out like 10 million electrons. And they are amplified, and then the counter counts these events. So this is also in the vacuum, but they're shielding around it and so forth. Next slide. So then the whole thing, there's a computer integration, like all the voltages and all sorts of things can be controlled from the program. So I can run it and like create the ions and see what happens and how the storage is going on and so forth. That's right, go on, yes. I have different programs for different aspects, and I think it's too detailed to go too much into details. Next slide. So this is a project I just completed. So this is like a new design. The electron gun will be on the bottom. So this idea will be, if you look back at the, you don't have to go back, but the design right now in the vacuum chamber is that I create the ions in the Paul trap itself. Yeah? And that causes some difficulties, which might be too detailed here, but now what I want to do is I want to create the ions outside and let them fly into the trap. Yeah? I've seen that in other people's work that they are doing that, and it seems to me a promising idea to solve some problems. And for that I machined the center part, and only in here the ions are created and then sucked out through the whole perpendicular. And yeah, this is fine. So this is in the test rig. So this is a Faraday cup, and this is the new electron source, only this little tube here, so it's more simple, and the electrons, like 1 centimeter away, they create the ions, and I think you've seen that outside when we lifted the paper. That's what we saw. So yeah, next slide. So here's the famous laser setup.
Still with the argon laser.
Still with the argon laser. Okay, forget the argon laser. This is a pump laser. So should I carry on, or you want to explain?
Go ahead.
Yeah. So the pump laser is going into the dye laser. You've seen that in the optic labs. So we start at a certain frequency, and the dye laser is tunable. A dye is a dye, so it's kind of, it has a whole range, and depending on the position of the mirrors, a certain frequency comes out, which is tunable. So then it goes here, it's frequency double, this here is for stabilizing, and then frequency double, now it's blue, but it's actually UV, and then it goes into the ion trap. And next slide. Okay, this is again the optical table many months ago, optical table now, one more. Optical table with a happy scientist. One back. Yeah. So you've seen that, and so here are all the pump laser, the dye laser, the frequency doubling, all being set up. Next slide. So this is a list of what needs to be done, and if I would keep thinking, and if you give me more time, I might be able to find some more things that need to be done. But the next thing for Marcus, I think all the laser tuning, getting the pump laser ready, then tuning the dye laser, the stabilizing loop, the frequency doubling. This is quite a lot of work. Then shifting all the vacuum stuff and all the cables and everything into the other room, integrating the two systems, the laser system and the trap system, solving all the problems connected with them, temperature, how things stand and whatnot. And I think ordering some more windows with different properties and a bunch of other things that are on a list to do. Then optimizing the ion storage, that's what I'm working on right now. And something that we can do after integration and stabilizing is optical sensitivity. Even if everything works, then a few or a couple of orders of magnitude still need to be done to fine-tune, to really get to that very, very narrow. So let's say first we see the ions, but to actually detect this difference in spin up and spin down, that I think are 6 or 7 orders of magnitude difference. So it's much easier to just see the ion, but to see the difference, spin up and spin down, more tuning has to be done. So, and then the optical detection of the ions is positioning, tuning, and fiddling. And then, of course, that's the last stage is the magnetic field and the spin flip detection. Now, when I think about it, the camera, getting the camera and putting the camera, and that will be all things that need to be done. So we nearly finished now. So if everything is done, then we see that picture, and then the real experiment starts, because then, next slide, then we can do what we all came together for, to see how the mind affects the spin. Next slide. And so that's the outlook, the mental control. So I think first we do it in the lab, next to it, with local participants. It's easiest to call from people to come out from Berlin. Then another thing which is easy at a distance, you know, Ron and his friends, they can give it a shot from, because the camera picture can be projected on, or can be seen on any computer worldwide, you know, there's no problem.
Yeah.
So if you can link to and make that spin flip, fine. So, and then of course getting promising PK candidates out here. I mean, of course, if the local participants can do it, then we might not need to get our promising PK participants, but if we need more help from more psychically advanced people, we're going to take it. I personally think that it's a challenge to get the whole thing running, but it has been done in many other labs before, like 30, 40, so I'm confident we can do it here. But it will be a challenge to get the mental link going. I'm confident we can do it, but it's a learning curve. So we need at least a couple of months to tune in. Because that's something really new that hasn't been done anywhere. But
With mental link being what do you mean by the mental link going? You mean?
yeah, if you, let's say we see the ions
Right.
and the spin and everything, then to sit there and to actually flip it.
Oh, yes.
That mental link. Get that going. That will take a learning curve.
Maybe we need also to do some work on the conditions of mental influence.
Absolutely.
Yeah, that's what we try to do with the other experiments.
Yeah. yeah.
Thorsten might be our first spin flipper.
Maybe. I'll try. I'm probably one of the first who has a chance to.
Yeah.
But didn't you say you were able to alter the distribution of ones and zeros from the random number generator?
Yeah.
All right.
Yeah,
Well,
after
that's
some learning I
actually-
could do it.
That takes far more energy to change those ones and zeros than it does to flip the spin.
That's right.
Who was it? It was one famous physicist. If he came to a lab, everything would break.
I
Was
think
it
it was
Boston
Pauli.
Pauli.
Yeah,
Pauli.
Pauli.
But he's not around.
No, he's not
he's not of any danger.
He came
But,
by his spirit.
huh?
Everything breaks down.
It's called the Pauli effect.
Yeah, yeah.
Have you thought about the peer reviewing of this whole procedure? I once spoke to Ron and I thought maybe Mr. Schüssler can even do this peer reviewing of here or whatever, but I think it's a very important part of the whole procedure to make a peer review of it.
Oh, listen, once we're successful and people can spin flip, then we have another task which is just as formidable, and that's getting it published in the hard science journals.
And then it's peer
It's
reviewed.
not going to be
Yeah.
easy, but it's possible.
But that's really
It's
important to think
possible
about it
that the former department head might agree
Yeah.
to come witness it and in some way make a public declaration. It's
Well,
possible.
we get the Valley check. There's a very senior scientist from the Fetzer Foundation, and I'm sure they send him out here to check us out. And that will be a very tough peer review, you know.
Okay.
So
But we also try to publish the setup. Setup.
Yeah, sure.
yeah,
Part of
that's,
it.
we have a publishing strategy, and that is basically to measure the spin of the magnesium, so the difference in the magnetic field. I'm not sure if anybody has done that before, so we check that out. And so we might be able to measure some normal physical parameters, i.e. tuning or let's say calibrating our apparatus to
Yeah.
a standard, and be able to publish that in a normal journal,
Yeah.
and then they can see the whole apparatus, and they can clarify before we do the mental influence
don't
that
tell
it's
them
a
anything.
proper apparatus and that it's physically okay.
Yeah.
Because I think we should do that before.
Yes,
Yeah.
sure.
Because otherwise you get the people who don't like mental
Exactly.
influence and they, you know, they want to avoid that. I think next
No, I
slide
agree
was
completely.
probably
We have to worry about the publication strategy now, and how are we going to go
Yeah.
about doing that, because we're going to encounter so much resistance.
Exactly. That's
So,
what you said.
Yeah, but we also have help, and I think it's an age. I mean, you know, you can put the on the X files. You know, that you can get out the word, and people can read it before the peer review people think it's good. That's what everybody does these days. You know, there's a kind of a preview where you can put it, and people who are interested, the word spreads, and they look at it. So that's one part, and the other part is to get into major publications, so to have more credibility. But I think getting the word out is easy and the most important thing. And if it comes into credible journals, great. If it takes time, it takes time. You know, that's a whole different and difficult arena on its own. But I'm pretty sure if it's all successful, it will make its way and the word will spread. Yeah, because we have contacts and people are interested, and word of mouth is always the most powerful.
well, particularly if you publish this early result of just detecting the ions or whatever you're doing in the standard physics journals, that will help a lot.
Yeah.
Yeah,
That
well,
will help a lot in building credibility.
And
downstream.
Hans agreed to help us there if we don't mention anything about
Mental.
consciousness.
Mental, exactly,
Yes.
exactly.
Yeah, you should not be on the blacklist before that.
Yeah.
okay, any more questions?
Yeah, are there any more questions?
Could I just ask two questions, but maybe you've answered them already. As you know, I'm not a physicist, but I'm very interested. Could you please tell me where you want to go? What would you be happy to show to the world as the end result of a series of experiments? And the second is, what have you already found out and can produce on the road, on the journey to this results? I understand you have done outstanding experiments where you do wild things in your, you know, these 4 rods and in that trap and that vacuum thing.
Yeah.
But what do you want to communicate to the, what is the end result you would like to communicate? Is it that light switch of Christian? And what have you, or what can you communicate already on the journey now?
Tell them about the Morse code or something.
Yeah, well, the first thing is that, you see, it's a very physical apparatus, yeah, with the light and everything, yeah. And so for normal scientists, you cannot, they don't know that you can flip the spin with the mind. That's something that is not in the textbooks, and it's not known to them. There's no theory for that. It's blank, yeah. So and in contrast to the other experiments that we were doing, where you have an influence over the mind, if you have an influence on the mind here, the spin will not flip on its own. Yeah? So we hope that it's a very clear thing. You know, like if you flip it on and off a couple of times, that's something that cannot just happen. The chance of that happening is outnumbering anything in the universe. Meaning it's impossible. Yeah? And if you make it 10 times, the number is really astronomical, beyond astronomical. So it's a very sure thing that it's only this influence. It can be isolated, and that's attracting to physicists, because the random numbers, there can be other reasons, and you don't know exactly how the process is happening. Yeah. So now you have an event on a single so-called quantum object, one electron, one ion, and not many. So it's like clear. And there are not many other or no other explanations for that.
Let me add to that. For example, you could use it to send messages by using your mind to make the fluorescence last for long and short periods. You can send a Morse code message with your mind. You could send a Morse code message sitting next to the machine, and probably from across the town or across the state. You could probably still do it once you learn how to do it next to the machine. It could be a form of communication which, for example, could go right through mountains and oceans and things. You have a submarine you're trying to reach 600 feet down below the surface of the water, halfway across the Atlantic. You could use this machine, you see, in the sub, and use your mind to send a message to the machine.
Let me add why I'm interested in the experiment, because I think it addresses your question exactly. What I want to demonstrate and think is that consciousness affects the material world. That the material world, this physical universe, is made up, according to physicists, of atoms, mass, fields, but consciousness is not a part of it. So what I want to demonstrate in this experiment is that consciousness affects matter in a way that's so clear that something else is going on that none of the physicists have been able to explain. That consciousness sort of sits above and is more fundamental unit that can drive the behavior of matter in our physical world. Now, what's so beautiful about this experiment is we're doing it in a way that the physicists will understand. So what I'm hoping we'll be able to do is convert more physicists to this understanding, because when they see what we do, some of them are going to say, oh my God, what does this mean? You know, those that don't believe that consciousness really can affect the physical world in this way. And so what I'm hoping to do with the experiment is to convert some of those physicists, some which are nearby, who are open-minded, that there's something at play here that is very, very important to understanding what are we experiencing in this life? What are we really experiencing? And how does consciousness affect that, and how does consciousness affect matter, and maybe how do we even create events with our consciousness? So these coincidences, I mean, that's downstream, but I mean, most of the people in this room believe that, you know, we all came together because somehow our consciousness communicated outside of the physical world in a different realm. So I hope that we will be able to convert more physicists to plan their own experiments and advance their own theories and really start thinking about this, because I think we'll be able then to greatly accelerate our understanding of the physical world, or the rate of scientific discovery. So I think that there's a tremendous amount to be able to do that, and that's why I'm so excited about what we're doing.
Yeah, it's actually possible with this experiment to investigate how consciousness interacts with matter, because you have the single quantum object. With all the other experiments, even Dean Radin, he's using quantum objects, but he's using a bunch of them. He's doing these experiments with laser interference, and he's not able to actually see what's happening to the photons. And so there's no way that he can understand what's going on. He just can show that there's something going on, but his experiment is not, he can't explain anything with it. And with this experiment, you can start about thinking of theory and start to describe what's going on.
In Dean Radin's experiment, you have light coming from a laser which goes through a double slit, like I showed in one of my pictures, creating a bar pattern. And you try to change the bar pattern with your mind. He's working with about 1 trillion million photons per second, traveling about a foot, which takes him about a nanosecond. So you're working with an incredible number of photons, and you only get to look at each one for a nanosecond.
Yeah.
We got one atom, we can look at it for 24 hours. We really get to know, we can name it.
Yeah.
Mhm.
And that's a real advantage. So
We'll
this
call
is
it
the,
Marlowe.
and last when I was for the last time in India, when I was the last time in India, I talked to Professor Shukla, and he also said this might change everything because people might think about what they actually think about. What their thoughts are creating, like how their thoughts are creating with their environment and with every other person there, and so this might change, everything. So if the people starts to understand, if people start to understand that there is more than just the material world, and every person's consciousness matters, then there might be change.
I met Ron at the Seth conference. We were at the Seth conference together, and some of the Seth, so this was before we got interested in the physics experiment and all of this, but in the Seth conference, some Seth says even an electron has a consciousness. So in other words, when we're able to do this, it's a sort of our consciousness perhaps communicating directly with the consciousness of the electron and asking the electron to do this, and it will participate. And there's so many amazing things, as I said, that are so far out from anything anyone really hardly believes, but that was kind of my awakening to interest in some of these areas of what is possible with consciousness. What can we really do if we everything from consciousness creates weather patterns. We're creating the weather patterns with our consciousness. There's just so many things that we don't really accept in general that are possible. And this will be sort of the first step in getting people to looking at phenomena like that.
Okay. Are there any more questions?
So maybe the Indian rain dance where they dance.
One more question.
Yeah.
Is there any chance that a particle from the universe, like a positron or neutrino is the name, maybe influences the spin of the...
Yeah, so it is not really right that there is no other way that or maybe Bryan can explain it better, he's the theoretical physicist.
Now maybe I can answer.
What did you do?
Question.
I can do
Well,
it.
of course there are more details to it, yes? The lucky thing is that a lot of the things that usually happen and will do any changes to our setup, they will knock out the ion, yeah? So like so-called rest gas atom will hit it and it's then not an ion anymore, then it will not be there anymore and it will be gone. But that can be detected because there is like a little bit of light coming even from, because one thing that is a lot more detail is that it's not so clear to distinguish. So let's say there is a chance, depending on the distance of the two energy levels, that even though the spin is down and it should not be fluorescent at all, it will take up one of those laser photons. So let's say even the one which is not there, it will shine a little bit. So the difference will be the one is shining brightly and the other one will be hardly detectable. But at least we know it's there, so we can distinguish from it being knocked out, you know. So, and yes, a particle that would fly by in the exact right path, it would be like saying there could be a planet flying by, our planet, which can happen, you know, probably same likelihood, and it will flip our axis. And instead of spinning like this, the Earth will spin the other way. That is possible. And it might have happened before that something flies by. But you see how exactly it should have to fly by. Very closely, if it's far away, it will not do that. If it's too close, it will knock us to pieces. So in the similar thing here, if a charged particle will fly on a very distinct path, it might flip the spin.
And there
But I think, we have to, if we use something like a Morse code and we conduct like a message or something like that, or if we do 10 in a row or something like that, we can eliminate that, because that will be like a single event. It will not come regularly. Yeah.
But the chance is very, very slight.
Yeah, I mean, so if I said there is no other way, this was a simplification. There is more details to it, but it can be narrowed down a lot, like things can be excluded, and so it could be worked on if it's too much. I think even in the beginning it's a chance, because if we don't make the magnetic field too high and the distance is low, it's still a statistical event. So we can kind of transit from the random number generator to the single quantum event. Yeah? So it's a chance also to get to learn the apparatus and so forth, you know?
Yeah, and I wanted to add that for a spin flip you have to have that amount of energy so you can kick it out, you can kick the atom out, but to keep the atom in there, in a trap, and to make a spin flip you have to have this amount of energy. And I think neutrinos are not the right particles, because there are exclusion rules. So there are many quantum numbers for each quantum object, and you have to have the right quantum numbers for changing the properties. And I think the neutrino has not the right. It's not similar to a photon, and the photons do the spin flip, right?
What they did was they produced photons with spin up and spin down, coupled to the same wave function, spin down, spin up.
Yeah.
They were able to use the photon spin, which is twice the spin of an electron, but they were still able to demonstrate the effect.
Yeah, that's right.
But he's right, it is possible, but there are much more likely other effects that we don't want that happen more often, but it would be possible.
I would say that
but very, very
you begin by flipping the spin, flipping it back, flipping and doing it, like you say, maybe 10 times. Then you know what you're doing.
Yeah.
Now, to be really convincing, you could send the preamble to the United Nations Charter in Morse code. Now, you know that that's not static.
Yes.
Yeah, so there are ways to come around that.
It becomes a very interesting philosophical question once we're successful in doing this, because then the physics world wants to replicate the results with tests throughout the world. Well, if consciousness is affecting matter, then the consciousness of the experimentals is affecting the outcome of this experiment.
True.
So that it would only be then a physics lab that was somewhat like-minded would be able to replicate the results, because I think, you know, perhaps consciousness is affecting of the experiments is affecting the whole outcome of the process.
Yeah, maybe, but they had experiments with a peer lab, and it's like this: those who are neutral, they cannot do much, but those who are very much against it, they are very emotional, they also have a chance of doing it.
Yeah. Well, but it probably will sort itself out anyway, because these experiments are difficult to conduct. So who is going to look into it initially will be those that are like-minded, open-minded in doing this. So there will be initial confirmations from other laboratories, and then there probably will be a wave of refutations or discrediting by other labs who don't like this idea. So it will be a very interesting time to see how the ideas play out over time.
Well, there are always critics, but I think the wonderful thing is that things that work will be used, you know? So if it works, it will be used. And critics cannot do anything against that, you know?
The end result will be our own journal for this kind of physics, our own funding from the government or other world governments for this kind of research, and postdocs who don't destroy their careers
Just work in this corner.
by working on this problem.
Well, we are happy to work on this, you know, we don't fear.
You're fearless.
You're fearless.
True.
Pretty well.
So then we're gonna have a coffee break. Yeah. see that. And the scientists.
One day we'll see you on the walls there.
All wrong.
All wrong, yes, all wrong.
On the wall there.
The good thing is we both don't do it because of that. Or you could care less, couldn't you? I'd rather not wait.